So here we're going to talk about increasing and decreasing functions. This is going to be the main application of the differentiation, which is just a procedure that you've learnt up to now. Differentiation is useful for finding turning points, we'll see that in a second, but it also determines whether at any point in time a function is either going up or going down. So if we look at these two lines here, it's clear that both of them are going up. And by going up, what we mean is that as x increases, their value increases. Here, as x increases, its value increases. Now you can see that these are going up in sort of different ways, but they are both increasing. And what is true if something is increasing is that dy dx, the gradient, is positive. I'm not sure if I've seen this notation here before, but that's a different way of writing it. If y is f of x, then we can either write dy dx is greater than 0, or we can write that f dash is greater than 0. F dash, or f prime it's sometimes called, just means differentiate f once. Obviously this notation here is not quite as clear because it's not telling you what you're differentiating with respect to. So this notation here is often used in mechanics, but we also see it appearing here. Let's look at these ones down here. So first of all, we'll translate that statement in dy dx notation. That says that dy dx is less than 0. And we're now talking about decreasing functions. Both of these functions here are decreasing. And the reason is that for both of them, as x increases, the value of the function is going down. Here, as x increases, the value of the function is going down. So we'll group those two together. They are increasing functions. And these two down here are decreasing function. And what tells us whether they're decreasing or increasing is the value of the gradient. Now, one thing just to mention for later on is that you can sort of see that these two have something in common in terms of their shape. And also these two have something in common in terms of their shape. Now, these ones here are both what we call convex graphs, and these two here are what we both call concave. There are other names, for instance convex is sometimes called concave down, but we'll call these two convex and these two concave. Now, what determines these shapes is to do with the value of the second derivative of d squared y dx squared. Later on we'll use that for a different purpose. But for now, notice that the principle or the idea of being increasing doesn't matter how it's increasing as long as it is, and decreasing doesn't matter how it's decreasing as long as it's going down as x increases. If you ever see the word increasing function, you should immediately be thinking gradient is bigger than 0. If you ever see the phrase decreasing function, you should be immediately thinking that the gradient should be less than 0. These graphs here are not very interesting because this one here is always increasing, this one is always increasing, this one is always decreasing, this one's always decreasing. In a second, we're going to see some functions where you have to determine when it's increasing and when it's decreasing. Something to note in advance is if something's going to change from being increasing to being decreasing, there must be a point in between where it's got a gradient of 0. So now we'll look at an example. And down here is a question. This is quite an involved question. It probably asks you more than you'd be asked in an exam. It asks you to investigate 3 different things. An exam question would usually only have one of these, but it's good practice for now. So, this question says, find when the following curves are increasing, decreasing, and stationary. We know straight away that increasing means that dy dx, the gradient, will be positive. We know that decreasing means that dy dx will be negative, less than 0, and stationary just means that it will be 0. It won't be going up and it won't be going down. Before we actually investigate this particular function here, it's quite an awkward one to draw, just for a second think about this graph down here. So if I drew something like that, for instance, okay, that's a kind of classic cubic shape. Now for that particular graph there, let's look about when it's going to be increasing. It would be increasing over that little part there, and it would be increasing over this part here. Now they're increasing in different ways actually in both of those parts of the graph. This is actually a concave increasing, this is actually convex increasing, but it's increasing here and it's increasing there. Now, in the in-between part, this bit here, it is decreasing. It's going down. As x goes across, y is going downwards. And just in between, it changes from being an increase function to being a decreasing function. And here, it changes from being a decreasing function to being an increasing function. We call those stationary points. It's briefly pausing. Okay? In this case, this is pausing what we call a maximum. Here it's pausing at a minimum. So let me just maybe add on there. Now, For cubics, you would expect a maximum and a minimum. You know what a cubic looks like. For a quadratic, you would expect either a maximum or a minimum. When you're presented with something like this, that's much harder to make a decision about. So we actually have to do the algebra and do the differentiation to investigate it. So I know that increasing, decreasing, and stationary are all statements about the gradient, about dy dx. So the first thing I'm going to do is I'm going to work out what dy dx is. So I'm going to change this piece of algebra into a piece of algebra here which is explicitly in terms of powers, so it'll be much easier to differentiate. And when I do differentiate that by bringing the power down and decreasing the power by 1, I get this expression here. This is the gradient of the function. If you plug in any value of x into this, it will tell you the value of the gradient. It will tell you how steep the graph is at that particular point. If you plug in a value of x and get a negative answer, it's decreasing at that position. If you plug in an x value and get a positive value, then it is increasing. I can't remember if I just increasing or decreasing, but it's increasing if it's positive, decreasing if it's negative. We're not going to just try random values and find out where it might be increasing, where it might be decreasing. We're going to actually set up an inequality. So the first thing I'm asked about is increasing. So I know that this is increasing when dy dx is bigger than 0. So I'm going to take the expression for dy dx and set it bigger than 0. I need to solve this inequality. So I bring this term across, and everything I do from now is to try and get the x's together on one side and the numbers on the other. So the first thing I did here was to times through by x to the half. That gets rid of this. It might help to note that that thing there is the same thing as a half 1 over x to the half. That maybe makes it more clear as to why I would times both sides by x to the half. But when I do that, and when I also times through by the 2 as well, I get this expression here. This is really the same inequality. So let me just go on to the next slide. So I had actually x to the 3 over 2 up there, and this was a quarter. And then carrying on with solving this, this is really just index work. I want to get rid of that power of 3 over 2, so I raise both sides to the power of 2/3. Some people might square and then take the cube root, but that's exactly the same thing as what I've got here. At that point, again, a bit of index work with numbers. You've seen that earlier on. I end up getting that x is greater than 1 over the cube root of 16. There's not really very much you can do with that. So this is the kind of critical value, okay? Provided that x is greater than that, the gradient will be positive and it will be increasing. The second part of the question asks me about decreasing functions, or the decreasing part of this function. So it's decreasing when the gradient is less than 0. Now I've skipped out some of the working here, but it's exactly the same as what I've already done over here for the increasing one. Your initial statement would be that dy dx is less than 0. We've already got that up there. And that gives you 2x minus a half. X to the minus a half would be less than 0. And you could see that all the algebra you do with this will be exactly the same as the algebra I did over there. The only difference is that I would keep this sign here the other way around. So I find out this time that it's decreasing when x is less than that value. Now, even without going through any of the other work, you can see that between being increasing and decreasing, there is that magic moment, that exact point where it is stationary, where it has a gradient of 0. So, just change that. It's really important that that's 0, not 1. That is a stationary point. That is a turning point. That is a point where it's neither going up nor going down. It's just paused. And that happens at an exact value. You can't ever say that a stationary point happens over a range of values like these two. It's got to happen at an exact point. So we have, for a long period of time here, it's decreasing. It pauses, and then it begins to increase from every value from then on. So there's now another example of the same thing. This one's a little bit quicker. So looking at this function, I've got this thing here, a very simple looking function, but to differentiate it, I need to expand it out. So I'm working with y equals x plus x squared. So because I'm being asked about increasing, because I'm being asked about decreasing, and because there's mention of stationary points, I must then differentiate. All of those are statements about the gradient. So I have dy dx is 1 plus 2x when I differentiate this. So this is an increasing function when dy dx is positive. So I get this rather more simple inequality, and I get this range of values there. It's going to be decreasing when dy dx, when this thing here is less than 0. Going through the algebra, you get that x is less than minus a half. And it will be stationary when dy dx is exactly equal to 0. Not greater than 0, not less than or equal to 0, but sorry, not greater than 0, not less than 0, but actually equal to 0, and that happens when x equals minus a half. Now, this is a good one for actually thinking about a diagram of, because everybody can draw a graph of y equals x upon 1 plus x. Okay, this is a quadratic. You know straight away that it's going to be a U-shaped quadratic because it's a positive x term. You could find its roots quite easily by setting this equal to 0, but I can see that it's going to cross the x-axis at 0. There we go. It's also going to cross at minus 1. And so if I drew it, I'd get a graph like this. And everything we've said now makes sense. It is increasing over this range of values here. Okay, so let's work out where that critical point is there. It's halfway between minus 1 and 0. It is at minus a half. If you plug in an x value bigger than minus a half, your function is going up. It is an increasing function. If you plug in exactly the value itself of minus a half, you get this critical little point down here. You get the position where the gradient is 0, where it's completely stationary. And in this section here, for all the x values less than minus a half, so when you plug in all of these values here of x less than minus a half, you get a function which is going downwards. You get a function which is decreasing, which is what this statement here says. This example here is probably the best one to start with if you're going to try and make sense of what the gradient is telling you. So, here's just a little statement which isn't a huge step up, but it is something people can find difficult. We tend to get so used to this expression dy dx, we forget what it actually means. What it's saying is it's talking about y. Okay? It's talking about the value of y. And it's saying, how is y changing with respect to x? Okay, you should really think of this piece of maths here as something which is acting on the y. It's what we call an operator. This is acting on y. It's asking you about y. It's saying, how is y changing with respect to x? Okay, you really can't be too careful with your notation. Okay, and you can't be too careful with your understanding of this idea either. So if we look at this thing here, this is saying, how is s changing with respect to t? You're being asked something about s, you're being asked what's its rate of change with respect to t. This has connotations in mechanics because s is the statement for displacement and t is time. So this is saying, how is your displacement changing with time? And we know that as the velocity. Okay, so if you write ds dt, you're actually really writing down velocity. So this is a bit of mechanics revision. We can then say, okay, well I know how the position of the displacement of the particle is changing with time. You might also be interested in how is its velocity changing with time. Now, even as just an item of vocabulary, we know what we call the rate of change of speed or the rate of change of velocity. That is called acceleration. If you're interested in how your velocity is changing with time, you are interested in your acceleration. So this is another way of writing acceleration. This statement here says, how is your velocity changing with respect to time? As we've seen before, just a reminder here, if dy dx is negative, then y is decreasing as x goes up. Okay. So let's scroll down and look at this example here. So this says the area A, we've given a label to the area, of a blot of ink is growing so that after t seconds, its area is given by A equals 3t squared plus 1/5 t. And we're told that the units are centimetres. I presume that should actually be centimetres squared. Okay. And it then says, find the rate of increase of the area after 2 seconds. Find the rate of increase of the area. We are interested in the area. So you would straight away write down area. It's a question about area. And specifically asked at the rate of increase. Okay? So the rate. As soon as you see rate, we're talking about a gradient. How something is changing. So I am asking, how is the area changing with respect to time? Okay? So I need to find out dA dt, so I go back and I differentiate this expression. So I get this thing here. This is my derivative. This is the differential of A with respect to t. It is dA dt. It is how A is changing with respect to time. There are lots of different ways of saying the same thing. And we're asked about a specific point at 2 seconds. When you plug 2 into this, expression here, you will get the gradient at time t equals 2. And the answer we get is 12 1/5. So that is the rate of increase. And I should make sure I've got some units on that. That's 12 1/5 centimetres squared per second. That's its rate of increase at that particular time. Let's try and think about a time when it maybe would be decreasing. Okay. Now, the problem with this is you have to be quite flexible with your times. The only way you're going to get a negative number here is if you put a negative time in. So from time t equals 0 onwards, this is always increasing. But if you're allowed to put a negative time in, you would get a decreasing rate of increase. Okay, so here we have another question which is going to be talking about derivatives, whether it tells you about them increasing, decreasing, or whether it tells you where stationary points are. And this is again a mechanics application. This is talking about something which is applicable to M1. So, I'm not sure why that hasn't come out, but here you are told that the height h in meters of a ball at any time t after it's thrown in the air is given by this equation here. Okay, so if you were to plug a value of t into this, it will be telling you how high up it is. Okay, so it doesn't tell us how quickly it's going, it doesn't tell us whether it's on the way up or on the way down, it just tells us where it is. Okay, so we're going to investigate some other properties of this. So here we're told to find the height of the ball after 2 seconds. Well, this is exactly what this expression is for. It tells you the height at a given time. So I'm going to plug in t equals 2 and I end up getting that h equals 19. So going back and consulting the units, I know that at time t equals 2, I'm at a height of 19 meters. Notice I don't know at this point whether it's on the way up or whether it's on the way down. Part 2 says find an expression for the rate of change of the height at time t. So first of all, you're going to get an expression out for this. You're not expecting a number like in part A. You're expecting a piece of algebra. A piece of algebra which, if you plug into it, will tell you at that value of t what is the rate of change of the height. Now, rate of change of the height. This is asking you about height. It's asking you to say something about h. And it's saying the rate of change, so we're asking for dh, dt. You're being asked, how is h changing with respect to time? Based on our conversation earlier, we know that the rate at which your height changes is actually your velocity. Okay, so when I calculate dh dt, involves me bringing down powers, decreasing the power by 1, I get 11 minus 10t. So, just out of curiosity now, we can maybe answer our question from earlier on. I didn't know at 2 seconds, I didn't know whether this, when it was a height of 19 meters, I didn't know whether it was on the way up, whether it was on the way down. Well, let's just briefly find out. Question didn't ask for this, but it's still quite interesting. So at t equals 2, I know that dh dt, which is its speed, is 11, take away 20, which is going to be equal to minus 9. And so that means that its velocity is in the downwards direction, so it's actually going downwards. It's already reached its maximum height and it's on the way back down. Okay, so let's have a look at the final part of this question. It says, find the time when the ball is at its maximum height and also find this maximum height. So when it's at a maximum height, I know that dh dt, which is here, will be 0. It won't be going up, it won't be going down, it'll be at its stationary point, it'll just be at its uppermost. So I'm going to find out when dh dt is 0, and I'm going to go and set 11 minus 10 to equal to 0, and I find that the maximum height happens when t equals 1.1 seconds. This links in with what we set up here. If it's t equals 2 seconds, you've gone past the maximum height, so we are on the way back down, as this bit of extra work showed us. So this question didn't just say find when it's at the maximum height, it said what is that maximum height. Now, it is asking you for a height. This is the expression up here which tells you about height, so you're going to plug this particular time value into this expression for height. And when t equals 1.1, we end up finding that the height is 23.05 meters. So let's just maybe draw a little diagram of this. So you throw it, it goes up, and it comes back down again. So it's thrown upwards at time t equals 0. It reaches a maximum when t equals 1.1. By symmetry, it will hit the ground again when t equals 2.2. It takes as long to go up as it does to come back down again. This particular thing here, this particular time of t equals 2, happens around about there. At this time here, it's at a height of 23.05, the maximum height, and here when it's on the way back down at t equals 2, that's 19 meters. So, just one more symmetry thing which might be interesting is, if this point here is time t equals 2, and we know it's at 19 meters then by symmetry, it's at 19 meters here as well. Time t equals 2 is 0.9 seconds after 1.1, so if I go 0.9 seconds before, I get 0.2 here. So the other time when it's at 19 meters is at 0.2 seconds.